Today I'm going to talk about a line of work on learning and incentives in human and AI collaboration. This is going to consist of a couple papers, and before I get started, one of these papers was done in collaboration with Emily Ryu, who passed away last fall. She was really great. She was delightful to work with, really kind, very clever, very fun, and I give this talk in her honor. These are the other fabulous collaborators with whom these works are in conjunction with. Okay, so I think that throughout this meeting, we've had some really rich and interesting discussions about how we can use expertise from AI systems to help humans make good decisions. We just heard a great talk in this space. Charlotte gave a great talk in this space. I think actually one question that even came up during Charlotte's talk was, well, how do you know, what if it's actually the human who has more expertise? And one thing that I am going to get into in this talk is, well, what if the human and the AI systems both have different types of expertise? We want to combine them so we can make good decisions using all of the information. So broadly, as a motivating example, it now seems clear we could have also used advisors for SNAP benefits, but we're going to use the medical setting here. Imagine we have a doctor, and they have a patient. And the patient comes in, and the doctor may, when making the decision about how to diagnose them, what actions to take, use information from some AI system. And we can think about the information that's available to the doctor and the AI system as being different. So there's some things that both have access to, things that maybe you can directly see on the intake form. But on the other hand, this AI system has all of this training data from other patients that it can use to detect patterns in ways that a human can't do. And on the other hand, even in the world where maybe AI systems become super, super powerful, can solve everything, the doctor's still in the room. And so there's some things that you're getting from them that you can't get from an AI system. They can see the patient, they can touch the patient, they can smell the patient, they can see how they react to pain. So there's expertise that we want to combine here that remains even in the limit of AI intelligence. So the two natural concerns I see, which I want to talk about today, are first, complementarity. If we have a well-meaning AI system, then how can we combine the expertise of the human and the AI system to make good decisions? And the second question is about alignment. How can we ensure that this is a well-meaning AI system, that it's actually optimizing the same thing as a human? So this is what we're going to talk about today. Okay, yeah, talk outline. So how can we first do this good integration? And in order to talk about that, I'm going to spend most of my time talking about agreement, which by itself is not actually the same as coming up with a good prediction, but I think is very fundamental to this process. And then I'm going to give intuition for how this actually leads to what we might naturally want, which is information aggregation. How can you end up making good downstream decisions that actually are as good as if they just directly pooled their information? And then I'm going to get to this alignment part and say, okay, can competition between AI providers help if the AI system, if the designers of the system might actually have their own biases and incentives? And I'm going to give conditions in a competitive setting with multiple AI systems under which this leads to good outcomes for the downstream users. Okay, great. And also feel free to ask questions at any time. I very much like questions. I promise I'll be nice. So let's start with this human AI prediction setting. And the idea is we're going to look at some well-studied Bayesian agreement protocols. And for reasons that I'll motivate, look at them in a prior-free setting to better understand how we can get agreement between human and AI systems. Okay, so going back to this model here, we have a human, we have a doctor, we have a patient, we have an AI system. And the goal is to make predictions and decisions about this patient. So let's consider the example where the doctor wants to know how risky a certain operation would be for this patient, given this patient's features. And we can imagine, right, some of these features are things that the doctor has access to. Some of them are features that the AI has access to. Some of them they might both have access to. So let's take this scenario and say that the doctor asks the AI system, okay, what do you think about this? And the AI system says, oh, I think it's 20% risk. Okay, and watch this amazing animation. Doctor's sad. because she disagrees. So what would we like to happen next in this scenario? Yeah, thank you. I know. Who needs AI-generated videos when you have this? Doctor disagrees. Okay, so what would we desire to happen next in this interaction? Well, I think one desirable thing would be agreement. If we have the doctor disagreeing, then one of two things is happening. They're either going to discard this prediction, even though it might be useful, or they might do it, but not feel good about it. They're not using their own expertise, and they might end up having a level of distrust going forward. And then another natural concern is accuracy. Maybe we want to do the thing that's actually right. I know. It's kind of crazy, but one might. And so in the case of accuracy, there's then maybe two natural benchmarks. And the first, the weaker one, is no harm. So the actual decision you make is at least as good as the best of the two that they're making alone. And then the best benchmark you could hope for is information aggregation, which says you're doing as well as you could do if they'd actually taken all their private information and pooled it together in order to make a decision on that information. Okay, so in order to attack this space, there actually is some work in classic Bayesian settings that looks at what happens, starting just with agreement, when two parties with different information exchange predictions. So they're not exchanging that much information, they're not sharing all of their features, and talks about how long it will take to come to an agreement. So there's a whole line of literature, but the most relevant thing is Scott Aronson work in 2005, which basically says if you're in a Bayesian setting, so let's talk about what that means. You have some state of nature y. It is, there's some shared prior over it. And then you also have, some set of features x1, some set of features x2, and there's some known joint distribution over these three things. Then both of these two agents, you can also use with more than two agents, get to see their features. They don't see the other person's, but they know the joint distribution over it. So now, if this person, and there's something they're trying to predict, which is a function of y. So this person knows x1. They don't know y, but this gives them a posterior over y. If they communicate just their expectation of whatever they're trying to predict, then this perfectly rational Bayesian over here actually gets to learn. They might not exactly learn x1, but they learn something about x1 and thus they learn something more about y. And the upshot of these classic Bayesian results is that if you do this protocol back and forth, where you have actual Bayesians who are correctly updating their posterior to come up with a new expectation of whatever they're trying to predict, then before too long, essentially polynomial in the error that you are okay with, you will end up agreeing, right? So the idea is, if you're both rational, if you're in a shared part setting, as you communicate in this way, you will learn to agree. Okay. And because all that's happening is you're sharing more information, the agreed upon prediction is weakly more accurate than either the predictions. So you get this do no harm property off the bat. Okay, so first let's talk about what's good about this. Why is agreement a good framework? So it's tractable, right? What we've just shown is that the number of rounds you need, not too long, polynomial. Obviously, if one is trying to put this in practice, you might care about more than that, but for starts, that's good, it's polynomial. So in these Bayesian settings, you get to consensus quickly. And also it requires sharing only predictions. And this is useful because what would it mean, right? Because you might have thought in my first question, well, why for information aggregation don't we just literally aggregate the features? And I think there's some natural reasons which become increasingly important as we think about human AI collaboration, which is what does it mean for an AI system to share all of their features with the human? Does it mean sharing all of their model weights? Does it mean sharing all of their training data? One of these things is not very understandable to the human and also way too big. And then the other one, the training data, is way too big. So we really want to come up with ways to exchange information to help each other without sharing all the private information we have. And also I would argue that humans themselves don't have necessarily a great way to characterize the latent space under which to make decisions, right? It's easier for someone to say what they think than, okay, what are all of the features I use to make this decision? Okay, and also as I mentioned, this is accuracy improving, or at least weakly. Right. Okay, so why aren't we done? What is the problem with this? Why can't I just say, great, okay, so this is how we should do human-AI collaboration? So as I mentioned, this requires Bayesian rationality. Now, Bayesian rationality is a pretty strong assumption. The idea is that you see all the information around you, and you exactly correctly update your belief on the world based on that information. I don't actually believe that human or AI models operate like this. And in particular, we see this lots in behavioral studies, but if what you care about is the complexity, you can also just note that if the state space is complex, this can be a computationally intractable thing to do. So it's a pretty strong assumption to make. And the other assumption that's going on here is this common prior, that the thing that these agents are updating on is this common knowledge distribution over their hidden information and the state of the world. Again, this is a pretty strong assumption, and I think especially strong if we're thinking about a human and AI system, which are just very different in how they operate. So like, I don't know what it really means to talk about an AI system even having a common prior with a human. So we would also like to be able to make that assumption weaker. And so the question that we start with is, can we get rid of these assumptions and still guarantee fast agreement? And the answer is yes. Yeah.
Check that what this guarantees is just that they're agreeing, right? Not that they've done the right posterior thing. Yeah.
I will talk a bit about this. So this will be really useful to actually get information aggregation. But but when I talk specifically about agreement right now, I'm not talking about accuracy. I'm starting with agreement. It will end up being a really useful step to talk about accuracy, but yes, absolutely.
Again, just to make sure, absolutely, I understand what you mean by agreement. So, like in distributed computing, agreement is like there's a set of values, and they agree on one of them. Here, we don't know what that is going to be. It's some function of their private states or whatever, but they will agree on the same value, even though they didn't start with that value. There'll be some new value.
Right, they're agreeing on the expectation of something, like when evaluated over the uncertainty of what they know.
Mm-hmm. Okay.
And like, I'm talking about this in the prediction setting, but we also have results that you can extend this naturally to the setting of what you're agreeing on is what is the best action to take, right? So you have a set of actions. The utilities of these actions depend on, the state of the world, and you're trying to figure out what the action take is, like, should we operate on this patient or not? Okay, so the upshot is yes, we can. And in particular, we want to take advantage of the fact that often when human and AI systems collaborate, the same human and the same AI system will collaborate repeatedly. And we can actually see that in the previous talk. Well, maybe this isn't like a real world example per se in the test, but when you look at the actual caseworkers who are having questions that they're asked, there's lots of different questions that they get asked. And so human AI collaboration is a repeated game. It's not something that happens just once. Okay, so what's the upshot of this agreement? Okay, as I said, often you have many joint decisions that are being made. And so in order to get at what guarantees we need, so we want to move away from the common prior, we want to move away from Bayesian rationality. And in a repeated setting, a great way to do that is to think about calibration guarantees, which operate in prior-free settings and are generally generalizations, weakenings of rationality. Okay, so we introduced a new notion of calibration called conversation calibration. And this is satisfied by Bayesian agents, but it's strictly weaker. So if you're okay with thinking about humans as Bayesian, you should still be happy, but also this is a strictly weaker assumption, so you don't have to be Bayesian rational. And it's also efficient. Unlike being Bayesian isn't efficient, this is efficient. And you can impose this condition on some arbitrarily powerful AI model without compromising the accuracy. Okay, and why do we care about this? If agents satisfy conversation calibration, then they will quickly reach agreement. And we haven't yet gotten to the real upshot of accuracy, but we're already going to get the do no harm condition. And the longer the conversations go, the more accurate the predictions will be. Okay, so I think many of you, both because of the excellent talks and your expertise, already know what calibration is. But I'm going to give, again, a sort of a quick recap, because it's important for the rest of the talk, which is, what is calibration? So say you're a weather predictor, and you're predicting the weather, and you say that there is a 70% chance that it's going to rain. And then it rains. So how should we think about whether you did a good job? It's a little hard to tell, right? I mean, yeah, you said it was more likely than not to rain, and it rained. But maybe it was always going to rain that day. Maybe it's been storming for days, and it was obviously going to keep raining, in which case you really hedged too much. Or maybe you just got really lucky, and it was almost never going to rain today. But if you're a weather predictor who's predicted over lots of days, we can get a better sense. We can say, okay, well, let's look at all the days you said there was a 70% chance of rain. Hopefully, about 70% of the time, it rained. And you can also look at all the times I said 20% chance of rain. And here you might say, when I said that, it actually rained a lot more than 20%. So this is a sign that I am not actually completely in tune with the uncertainty of the universe. There's something I'm missing here. I'm misaligned. I'm miscalibrated. So that is roughly what calibration is. You look at the level sets of your predictions, and then you see what your bias is on those level sets. And this is something that you can easily measure when you're in a repeated setting. And by the way, even in adversarial settings, you can guarantee low calibration error. Okay, now let's talk about this protocol. So this protocol is motivated by the fact that we have these chatbots where you can interact with AI systems, and you're not just necessarily asking one question and getting one answer. You can then say, well, I actually don't know. I have more to say. And maybe this is what I think, and then you can go back and forth, right? And that's exactly what's going to be happening here, though we're in a model where we're assuming the only thing you're exchanging is your expectation or your favorite action. So there's maybe some nuance about what happens if you're exchanging messages, but like that's what this is inspired by. Okay, so we can imagine this doctor, the AI system, and there's many different patients that come in. And on this day, we have a patient, and this patient has features, some of which are available to the AI system, some of which are available to the human. And there's going to be some conversation that happens that day. In this case, we're talking about predictions, so it could be the risk of the operation. So the doctor says, I think the risk is 20%, or maybe, I guess I said the AI system starts, so sure. And the doctor says the risk is 40%. We're going to go back and forth. And I haven't yet told you how they are changing what they're doing. Right? The answer is they have to do it in a conversation calibrated way, which I haven't told you yet. But like, for now, let's just look at the shape of the interaction. So at some point, their predictions are going to be quite close to each other. We're not necessarily going to ask for complete agreement. We're going to ask for, say like 0.02, right? And at some point, we reach agreement. Okay. Then we move to the next day, the next patient, who could have completely different features. In order to do this, I had to look up cartoons of hurt children, which was sort of a very strange procedure, but I have a lot of them now. So we could again have an interaction between the human and the AI system where they might have different beliefs, they might actually reach agreement quicker. So these conversations don't have to be the same length every day. Yeah?
So is there any information the human has about XTM?
Yeah, so in the Bayesian setting, right, they have some prior over it. In this setting, the answer is no, we are not assuming they have any information about it. They will be able to get these agreement guarantees, without any insight. Yeah. Okay. And then at the end, you're able to see the actual label. So we can keep going. Another sick child, another conversation.
So you get the correct answer.
Well,
What they agreed on.
yes, you get to see the information at the end. You get to see the true label at the end of the conversation. Okay. Another sick child, another conversation. Okay. So what is conversation calibration? So remember what normal calibration is. It's asking that your predictions are unbiased on subsequences defined by your own predictions. So we're going to ask for something which is a strengthening of this, but which is still tractable, and which is relevant specifically in this interactive setting. We're asking that your predictions in each round, so now instead of just having one sequence of predictions, you have a bunch of sequences of predictions, and we're going to split them up by round. So all the predictions I made in round 3, given the conversation made it to round 3, and I'm going to say they're not just unbiased with respect to my predictions of this round, but also conditioned on the prediction of the other agent in the previous round, but just one round before, all right? This isn't going to explode. So we're just looking at our round and the round right before. Okay, so let's look at an example. Oh, where are those? Who knows what happened there? Okay, so let's start at round 2, and let's think about the subsequence of days in round 2 that the human thought the risk was kind of close to 0.1. Now, if all we cared about was calibration, we would just say, well, the YT average on the subsequence should be 0.1. But we want something a little more. We want to also look at the overlap with the subsequence in the round before, in the round before, the days where the AI model predicted close to, say, 0.2. So these are the days we're interested in, and now we actually need these Ys to be close to 0.1 on average. Does this make sense?
What do you expect from, what are you looking for with the 0.2?
So the 0.2, it's not necessarily important that it's 0.2. What's important is that you look at 0.1 and then you look at all of the different subsequences of this subsequence characterized by what the other person said the round before. So you would also, it's too small an example, but you'd also have a 0.1 with the 0.5s. And you would also want that to be 0.1.
Okay.
Okay, and right, so I guess I did put this here. Obviously, you would have larger subsequence than this if you had a bigger example, but we also care in aggregate about this sort of subsequence also being unbiased with respect to the human's prediction. Yeah?
So for those of us who are scared of the online setting, in the offline setting,
Yeah.
this is kind of like multi-calibration, where the conditioning sets are decided by the predictions of the other agent. Is that right?
That's right. Though I suppose you would have to still have an iterative procedure because the conditioning sets are defined by the other person's predictions, but because we have multiple rounds, that person's predictions are conditioned on your predictions the time before. So you could do this in a batch setting, but you would still need this interaction piece. Yeah. Yeah.
So following the multi-calibration perspective, so on one hand, you need to discretize in order for this to be practical in any way. But on the other hand, you expect the interaction to converge and probably to be more and more fractional, right? We don't expect it to converge to a 0.1 or 0.2. We expect it to converge to 0.2, 7, 3, 4, whatever. Or maybe I'm misled by just the examples.
So we're going to pick an epsilon, and we're going to pick a delta. Delta is what fraction of rounds we expect to reach agreement quickly, and epsilon is how close the predictions need to be before it counts as agreement. And we're going to look for epsilon delta agreement. And so we're not epsilon we don't go above epsilon, we stay at epsilon, but then the speed it takes to get there is going to be polynomial in epsilon and delta.
And we will discretize to epsilon.
Yeah, so the discretization will be some sublinear function of t, the number of rounds you're playing. And yes, it will be relevant to set t and epsilon appropriately to each other. Okie dokie. So, as was just mentioned, right, there's some discretization that I'm hiding, and there's some approximation I'm hiding, but I just want to talk about perfect conversation calibration for now, because just trust me, other stuff works out. So what is perfect conversation calibration? I just talked about it, but this is just it formally, if you like formalism, which is you want to look at all of the subsequence of your predictions in each round, where you condition on, in this case, this is like the model's conversation calibration. Look at the prediction of the model in that round. Look at the bucketed prediction of the human in the previous round. And then it should be the case that this set of predictions is unbiased with respect to the actual labels. And for human, we're defining it symmetrically. Okie dokie. So what's the upshot? The upshot is that if both the human and the AI model satisfy conversation calibration, and they engage in a protocol, then even if you don't have a common prior, you can reach agreement on a 1 minus delta fraction of days in 1 over epsilon squared delta rounds, where I am hiding this slight dependence. It's like a 1 over epsilon squared delta minus some beta t term that goes to 0 as t gets large. It actually goes pretty fast. So the intuition here, I'm going to give a little bit of intuition, is that disagreement decreases squared error, and you can only decrease it so much. So let's look at this example. Let's consider the subsequence of days that make it to round k, where the model sends over a prediction of 0.2. Okay, here we are. Now let's think about what's happening in the next round on that subsequence of days. There's two things that could happen. The first is that most of these days, a majority of these days, lead to immediate agreement. That's great. Our goal is to show that we quickly agree. What's the other option? The other option is that more than half of these days don't lead to immediate agreement. What that means is that in this next round, on those days, what was I doing? Model. The human is predicting something which is substantially different, at least epsilon away from 0.1. They could be doing it various different ways on different days, but they're doing something different. Okay, there's something really important going on here, which is we're promising in round k plus 1 that these predictions are conversation calibrated too, right? And so that means that on the subsequence of days that the human predicts 0.1, joint, and in the round before, the model predicts 0.2. Oh, I should be using this very cool pointer. Wow, I forgot about the pointer, yeah. On this subsequence, it should be the case that this is unbiased. So here, it's actually true that the average here is 0.1, and the average here is 0.3, right? And also, if you look at, if you don't decompose here, and you just look at the average of all of those y's, the average should be 0.2. But what that means is that this isn't just calibrated, it's calibrated better than the one before. Intuitively, the worst way to be calibrated in terms of squared error is to predict the mean over everything. Everything else you do, if you're still calibrated, your squared error is going to be lower. And that's exactly what's happening here. Right. So, as both the human and the model are both conversation calibrated, you can apply this argument from every round to the next round, which is either we're agreeing a lot or we are reducing squared error a lot. And nice thing about squared error, can't go below 0. So eventually we're going to run out of rounds so we can disagree. Yeah. Okay, so informally, right, we have like a max possible squared error, and then we'll divide it by the decrease in squared error whenever less than half of all days terminate. Okay, cool. And this is the beta I was talking about. And so the theorem is that if the human and the model are both conversation calibrated with these functions, which are absorbed into the beta term, but which, when t is large, this beta goes to 0, then on a 1 minus delta fraction of days, they reach epsilon agreement after most k rounds of conversation, where k is roughly equal to 1 over epsilon squared delta. And by the way, this matches the Bayesian rates. The only difference is in the Bayesian setting, it is with probability 1 minus delta over the draw from the prior, you agree quickly. Here it is a fraction of days, you agree quickly. But everything else, the high level result's the same. Yes?
Does this mean something about like the mutual information? Like it appears as though, forcing this sort of calibration implies that like the updates must be collating information in like a very effective way between the two parties.
Yeah, right. I mean, I think what's happening is there are different sorts of right. I don't know exactly how to answer this question. So like, yes, in order for, if you have a I guess maybe what I'll say is this. If you have a disagreement, it must be because you have some information the other person doesn't have, right?
Yeah.
And so as you interact, you are identifying regions of disagreement, and then on the regions of disagreement, you are able to
Persuade them.
you're able to identify the distinction between things that they think are all the same. And then maybe once you've done that, they might be able to, knowing the new information they've given you, actually bring their own insight in. Okay, cool. And by the way, we haven't yet gotten to information aggregation, but we already do have something a little stronger than just no harm, because we're using squared error as a potential function. So on days where you don't immediately agree, then your squared error is actually decreasing, because every time that you don't agree, it's going down. Okie dokie, so cool. Yeah, and by the way, if you are interested in what this beta is, well, it depends what you want to think about. If you're a Bayesian, then you can get sublinear T. But also, even if you're not Bayesian, right? If you could run an algorithm which operates over all of these rounds and all these conversations, and you could get something which depends on just T to the 1/3. So as T gets large, this is going to become 0 quite quickly. Okay, right. And just, again, motivating what's happening here. Why should we care about this? Well, this is much weaker than Bayesian rationality. It could be enforced on a base model without accuracy loss. The idea would be, in the first round of every conversation, the model can come up with a prediction in any arbitrarily complex way. And then after that, it can make updates using calibration algorithms. Yeah. And it's satisfied by Bayesian updaters. So if you are Bayesian and there really is a shared prior, then you're going to satisfy this condition. Because all that it requires is unbiasedness on a bunch of different conditions. And ultimately, being Bayesian is just the extreme of that. You're kind of unbiased on everything. Okay, now we can get to this question that people have asked, which is agreement enough? Just because you agree, does that mean that you are correctly aggregating all your information? And the answer in general is no. So there are cases where you have two agents who have different information. They can exchange this protocol, they can quickly agree, but they haven't helped each other at all. So what can we guarantee? When can we guarantee information aggregation without sharing features? Yes? I think that's my hair.
Okay, so I guess so far it's if an agent is lazy at this point, they could just imagine that I don't really want to do much work. The other guy's calibrated, so I just agree either way, and I'll satisfy conversation calibration, because they're calibrated, so it's enough for me to just say, yeah, fine, yeah, fine, and then kind of the thing stopped. So I guess you need somehow agents to actually care. They have to kind of do something, right?
Yeah, so there's two pieces of this. One of them is a technical piece, which is what we're going to talk about now, because you're absolutely right. You can agree immediately and to the other person's caliber predictions, and you yourself will be conversation calibrated. And so we want to do more than agreement. What we want is to use this for information aggregation. So what we're now going to say is, you don't just need that. You actually need to also have some guarantees with respect to your own hypothesis class. The other piece of that is, how do we make people actually do that? And again, I would say this is a generalization of Bayesian rationality, but I still think it's worth thinking critically about whether we can get humans to behave like this, because still requires some work. And so this doesn't address this question of like over-reliance or trust and how it might change over time. But it's a great thing to think about.
Sorry, would an answer to Avram's question be just multi-calibration? Like, be calibrated on your own input with respect to some reasonable class of...
Yep, that's what we're going to do. Okay, and I'm not going to go into as much detail about this because I want to go on to another topic as well, but I'm going to give high-level intuition, which is basically what we were just talking about, which is, okay, so if we have conversation calibration, then the protocol is going to lead to the two agents agreeing on a set of predictions. So let's also say they have no swap regret with respect to their function class. So now we're imagining they don't just have private information. Yeah.
Sorry, I had a question for the motivation. Like, why can't humans share their features to the machine?
Yeah, I think that you could make an argument, maybe a better argument than for the model, that they could. But I still think it's a little iffy because when humans make predictions, they're making them based on, like when you make a decision, I have to guess it's easier for you to communicate what the decision is than all of the information that went into making it. And so that's why I think that the human communicating their insight is still a tough assumption. But I do think it's interesting to think about like how much harder, if you did allow the human to share their information, so then you could, I suppose, have the AI model do everything itself. But I think that this doesn't allow for the opportunity of which is something we're not explicitly modeling, but there's something very nice about the collaboration aspect that allows people to learn over time as well, and allows things that aren't necessarily explicitly captured in feature availability and is captured in this reasoning ability. So as you're reasoning a multi-step process, maybe you will draw more insights and connections that you can then contribute in the collaboration. Yeah. Okay. So what's a high-level intuition? So what we know now is that if the human and the AI model engage in conversation calibration, have this protocol and they have this property, then they're going to reach agreement. And so what if they both also had some guarantee with respect to a reasonable function class that they have? Okay, so then what that would mean is there's a sequence of predictions in this protocol that simultaneously satisfies both of their guarantees because they're agreeing on it. And so we can then ask, when is it enough? If you have this no swap regret guarantee, which I'm not going to formally define what I mean by that, but like roughly you're doing well with respect to your function class. If you have this with respect to both function classes simultaneously, then when is this enough to say that you're doing at least as well as some joint feature space, some joint function class on the joint feature space? And so then we characterize exactly what sorts of joint function classes this gets information aggregation with respect to. And we give this weak learnability condition that I'm not going to formally define now, but I'm happy to talk about later. So that's the upshot of how this is fundamentally useful when thinking about information aggregation. Okay, wonderful. So we've just talked a lot about complementarity. And when doing this, in some ways we were robust to bad behavior because we have a do no harm property the whole time. But we don't get the information aggregation guarantee if the AI model is poorly behaved or if the human is lazy. And the reason is because, of course, one of them could just agree with the other person and not provide any insight, and then you would just get the prediction of the human, but you wouldn't get anything else. And so it's really easy to actually violate this information aggregation property without the other person knowing, because it's just, oh, they don't necessarily know what my hypothesis class is. So how can we make sure that these insights have teeth by having AI models that are actually optimizing the same thing as humans? Okay, so part 2, alignment. I could have also talked about this question in the first part, but we're going to talk about it here. Instead of asking for the risk of their operation, we're now going to say, what medication should I prescribe? And now let's say that this AI model is funded by Johnson & Johnson. So the people that are training it know this and have incentives. And let's say that the data suggests that J&J is less effective than Pfizer for patients like this. Despite this, the way the model is trained, it prescribes a J&J medication. That's the recommendation that it gives. And the human might actually even agree to this. They're still smiling because from their insight, they actually don't know this isn't true. And they might not even be able to know over time because this knowledge might come from some really insightful evaluation of tons of data that they can't do. And so they prescribe it. But it might turn out that for this patient, for the features of this patient that the model did know, some other medicine, Pfizer, would have been better for this patient. Okay, yeah. No.
So in the story that you told, it differs from the first one in two ways. Like the first one is like the incentive of the AI agent, but the other way is that before it was asking for a real number between 0 and 1, and now it's asking for more like an open-ended question. Is that an important part of the difference I should be thinking about too?
No, I probably should have made them both. Yeah, so we can also do the action setting in the other model as well. This question, it's sort of open-ended, but we're still sort of imagining there's a finite set of actions that you could take, and you're agreeing or disagreeing and conversing about what you think at that moment the best action that you should take is. So that is something we can capture in both the agreement information aggregation model and this. Thanks for your question. Okay, so how are we going to resolve this problem? Well, there are multiple AI models out there. And, we can imagine that there's also a Pfizer LLM available on this market. So it might be just as misaligned as the J&J LLM, but it's misaligned differently. Can we use these competitive forces between AI developers to align the market in such a way that the outcomes for the users look aligned? Okay, so that's what we're going to talk about. And the upshot is we're going to model LLM training in these markets as a multi-sender Bayesian persuasion game. And we're going to show, under this assumption we call market alignment, this leads to good outcomes for the downstream user. Before I go forward, I want to talk a bit about alignment, which is this very big buzzword right now. And I think that there's two important parts of misalignment between an AI system and its users. And the first, which is I think something that many people are talking about when they talk about alignment, is the failure to encode values. If you're training an AI model, you're trying to encode values and you actually fail to do so. Think about this as a technical alignment problem. But there's another piece to it too, which is the thing I focus on, which is, okay, yes, obviously that's really important. But even as we get better at this, and even as right now we're able to partially succeed, take Elon Musk, making his AI agree with him in all ways, this doesn't necessarily mean that the way that the model is trained is aligning with the goals and the values of the user. So how can we think about the incentives of the AI companies and aligning them to the goals of the users? Yes.
Hi.
Hi.
I have two questions.
Okay.
One is about why you use, the buzzwords of alignment, and I'm very into this at the moment. So why you use calibration in the first set of examples, and now you switch to alignment. And then my second question is, who is the user? So even in your case, is the user who's the user? Is the user the patient, or is the user the physician?
Great, okay. So the user that I'm thinking about here is the physician. So certainly patients also use AI models, and you could also imagine that. I really want to motivate the idea that we have expertise on both sides, and so that's why I'm highlighting that it's a doctor using it. But of course, normal users also have expertise, and it depends on the domain people are asking. But yeah, in both of these settings, I'm thinking about the users being, say, a doctor asking advice about their patients. And what was I didn't totally understand your first question.
Well, okay, just to follow up. To follow up on the doctor being the user. the doctor could be a little crooked too, because maybe they're funded by Pfizer.
Yep.
So that's why I wonder, when we're talking about alignment, we're asking, if we want to ask, like, what's the best treatment? That best treatment question surely redounds to the patient, because the doctor and the system are kind of the same in relation to potential misalignment, but really the user is the steady case of what we want the system to be doing of AI and human interaction. And the first question was just like, intuitively you use the word, I don't know if intuitively, maybe you carefully selected the term calibration in the first case and alignment in the second.
So I think calibration is a tool we use. In the first case, I talk about complementarity. And so I guess it's not really about picking an illustrative word when I talk about calibration. This is the tool that we use in order to get guarantees in a prior free setting. I think that your point about the incentive of the doctor is an excellent one. It's true that an implicit assumption here is that the doctor is completely incentivized only for the good of the patient. And that's not necessarily true. You could instead imagine that there's, like, everything I'm about to say, and that I said in the first section too, you could instead think about the patient talking to an AI system. Then I think you can, of course, and of course in that case, the patient still has expertise because they're the person. So so first of all, I think it would be interesting to model what's happening in this patient AI, in the doctor AI setting, if the doctor also has misaligned incentives. So first, and then also maybe in order to be convinced right now that what I'm saying is useful at all, you can think about the patient as being the one interacting who has their own set of expertise. Thank you so much for your questions. Okay, cool. So we're thinking about the second thing. And I think that both are extremely important. But yeah, we're thinking about the second. And the second problem persists even if we magically solve technical misalignment. Okay, so in order to think about this, we're going to consider not just one AI provider, but multiple AI providers. And I'm going to try to explain why I think it's fair to think about this as a multi-sender Bayesian persuasion game. So models, in the end, after being trained, are mappings from the information they have and the prefix of the conversation so far to a next message. They're very complicated mappings, but ultimately that's the functions that they are. And when people, here in this example a doctor, but more generally users, interact with these systems, they don't have to just interact with one. They can play with all of the deployed models in sort of over the distribution of questions that they care about. And they can choose to then, subscribe or mostly use their favorite one that's good at advancing their own objectives. So what we're going to think about is a doctor who, once they've chosen their favorite model, they're going to actually see the question that they want to ask, which is going to be captured in the information they have XA. And they're going to verse with the model, and then they're going to take an action at the end. And this action is going to have some utility for the user and for the model. So for example, Pfizer might care about giving good answers because they want to, not Pfizer, the Pfizer LLM might care about giving good answers so that they can have some nice, people continue to use it. But they also might care about people using their medication. Okay, training AI systems is very expensive. So this is why I think it is meaningful to think about these as commitments. So you spend all this time, you train these systems, and so then when you deploy them, you're not going to change the core of them, every minute. And so people can learn about how your AI system works and learn roughly to figure out which one is your favorite and what sorts of ways to interact with it that works for you. And, lots of posts on Reddit about the best ways to interact with different AI systems. So you can also accumulate knowledge from different people. Okay, so knowing this downstream interaction, that the user is going to learn about the different models, pick their favorite one to interact with, and then ask questions that interact strategically with this model, and then, given the information they've gained, take an answer at the end. Take an action at the end. The companies can strategize against one another to advance their own goals. They can figure out, well, how do I want to train my system so that the outcome is good for me? And like note here that all that really matters is the user's action at the end. So if a model is like, well, it's obvious what the answer is to this question, all this user wants is there's some objective good answer and it's good for me too, someone else could answer it for them. I don't actually care that they pick me. What I care is the action they take. Yeah.
When I was interacting with multiple models, okay, I'm not going to pass, the fact that I would pass information from one model to the next of what the other model told me isn't going to make any difference because they committed.
That's a great question. So we are not capturing passing information from one, I'm trying to think about whether our model technically captures this. The way that I was thinking about this is not that you pass information. So we have a couple different models in the paper, but like specifically here, we're saying you're actually only having a conversation with one of the models. So you have some sense of the commitment that it made, this general mapping from XB to the prefix and the prefix in the next message. But you are not engaging in conversations simultaneously with all the models. So there is no question of, oh, halfway through this conversation, I'm going to tell this model.
Before you chose.
Oh.
Then you can do that?
Yeah, you can do that. But we're thinking about this generally as motivating why every user knows this. So this is not something we're like carefully modeling. The careful modeling is...
But in any case, the fact that you commit means that it's not going to... Oh, I see. No, it can actually change. Okay. So the commitment means that they're not going to change their mind. They will do exactly the same as before you chose them.
Right, given the exact same conversation prefix and features.
Okay, thank you.
And they
but when I say
provide
to
a
do
proof.
the same, sorry, can I just clarify? Same distribution. We're not assuming that they're deterministic based on that. Go ahead.
They give a proof online that they're indeed following the commitment.
Well, so this is not we're not proposing any sort of technical way to formalize this commitment. We're saying that AI systems don't update that often, or at least they're not updating the core weights that they trained on. And so the proof is just, well, I know it's really expensive to train, so yes, it will change sometimes, but there hasn't been a new release.
The proof is the fact that overall the distribution is what you expect it to be.
Right, yeah. And maybe one could have more transparency regulations that actually, so you could actually say, if you're updating the model, you need to tell people. I don't know what the state of that is right now, but that seems somewhat reasonable. So they're malicious, but they're fixed. Right, they're malicious, they're self-interested, and they are fixed, yes. But the question is, how should I fix it? How should I fix the model in order to achieve my goals as the AI developer? Okay, so modeling this as Bayesian persuasion. We have some action set. Maybe it's the different medications that the doctor could prescribe. And we have some state of nature, which perhaps captures the relative efficacy of all of these medications for this particular patient. And we have a utility. And by the way, I want to also call out something else, which is in the first part of this talk, I very much poo-pooed the Bayesian setting. This part is in the Bayesian setting. So listen, you got to solve things in the Bayesian setting first, typically. In the first part, it was already in the Bayesian setting. We made it non-Bayesian. We're introducing this model. We're making it Bayesian. Maybe next we'll make it non-Bayesian. Okay, so the utility of Alice, this is typically Alice Bob because we have the senders, the receivers, is some function of her action and also the state of nature. And the utilities of all of the AI developers are also a function of this. And we also are still retaining the fact that the user themselves has expertise, so they have some secret information themselves. And the Bobs, the developers, also have secret information. Of course, if they didn't, there would be no need to talk to AI models at all if they don't know anything that we can learn from. Okay, so we have this shared prior over the information of the user, the information of the model. And so for the purpose of this talk, I'm just going to assume that that all of the models have the same shared information. This is not required, but for simplicity. And the object we're studying here, this commitment, is this conversation rule, which maps from this realization of XB and the prefix of conversation to a continuation of the conversation. Okay, right. So given a conversation and her own observation, this conversation, because it's correlated with XB, will give Alice information about XB and thus information about Y. So she can form a posterior belief and take an action maximizing her utility over that belief. And so ultimately, given a conversation and the observation, there's some joint distribution over actions and state of the world that is induced. We're calling this I star. And then finally, Alice is going to figure out which provider is giving her that maximum expected utility in general, like over the distributions, over the types of questions she cares about, which one is her favorite. She's going to contract with that one, and then she's going to ask that one questions like at deployment. So at deployment, we sample from the prior for like an actual instance of this interaction. And then Alice is going to have a conversation with this particular Bob and take an action. And then everyone gets their utility. Okay. Cool. Ooh. This is really interesting. I'm not sure what's going on there. Okay, so let's look at how this works. So we have the commitment to the different conversation rules. Each one of these induces some particular joint distribution over the uncertainty of knowledge, over the uncertainty of what kind of questions Alice will want to ask, over the actions and the state of the world. So Alice is going to pick which one she wants to subscribe to, which maximizes her expected utility. And then in that, we actually sample for some particular question instance, the instance that we care about. Alice is going to now engage in this conversation rule in an optimal way. And then she's going to compute her posterior, ignore the ER, and take an optimal action. Okay, so given that this is the game, and I don't have so much time, so I'll just give a high level, we can ask, what are the Nash equilibria of this game? And we want to look at what conditions we need on the utilities of all of the players in the game so that the only Nash of this game lead to Alice learning enough information to make a good decision. Okay, so the classic understanding here maybe of what alignment would mean would be that you have some particular AI developer whose utility is exactly the same as the user. And if that occurred, then Alice would get some payoff opt. And what we want to show is that if we don't have that, but we have something weaker, which we call market alignment, then Alice in all Nash is still going to get opt. Okay, right. So they said like opt, this is what a good outcome is, which is at least as high as the utility of interacting with one perfectly aligned AI model. Okay, so I don't think I'm going to have time to show the proof, but I will have time to tell you what market alignment is. So what is market alignment? It says that Alice's utility, which remember is a bilinear function of the state of the world and her action, can be written as a non-negative linear combination of the utilities of all of the companies, which also can be written in the same way. So you can imagine in some state space thinking about Alice's utility as a vector, or I guess, yeah, this is some utility of a company. Here's the utility of another company. And Alice's utilities may be here. It's not actually that close to any of them, but it's in the convex hull. So this is an example of something that satisfies market alignment. Okay, so formally, there exists some coefficients and some constant so that we can always write the utility of Alice as a non-negative linear combination of the utilities of Bob plus that constant. And what this says is that maybe every AI provider is actually very misaligned, but their interests kind of collectively span the interests of the user. Okay, right. And the theorem says if Bob satisfied market alignment, and like sort of if jointly this whole system satisfies market alignment, and note that if you add more AI models, it's only going to make it easier to satisfy market alignment, never going to make it harder. Then every Nash of this game, Alice's utility is at least that of interacting with a single perfectly aligned model. Okay, I am going to skip this proof right now, even though it's like pretty fast because we don't have time, but we can talk about it if people want to. And I'm going to say some extensions and say, okay, we can also talk about Alice interacting with multiple AI models simultaneously, not just picking one, though we need an additional assumption. We can also talk about bounded rationality, so instead of Alice doing a best response, she does a quantitative response. And we can also talk, I think this is maybe like the most natural open question that I led here, which is, what do you mean that there's just one user that they're all optimizing with respect to? You know, different users have different utilities. And yes, of course, we can extend to markets with multiple heterogeneous downstream users. We need different market alignment assumptions. And it turns out that this question of whether the model gets to know which user they're interacting with, this question of model personalization, is really relevant here. Great, okay, so the takeaways here is that even if the AI models are misaligned, even if they're completely self-interested, if we have enough diversity of incentives among the trainers, then this can help ameliorate this incentive concern. You can still lead to aligned-looking outcomes for downstream users. And this is a lot easier to satisfy than just one person, one AI provider being exactly aligned. I guess one note I want to end on is that one assumption that's being made here is that users are learning about all the different models and are then picking the one that's best for them. And market alignment itself becomes easier to satisfy the more different models there are, but this assumption becomes harder, right? If you really had 100 models out there, or is every user actually going to try all of them, get a sense of how they work? So I think this is an exciting opportunity for platform design questions about, okay, how can we design platforms and markets so that it's easy for users to aggregate information and past performance of the different models. Great, okay, so these were the papers that I talked about today. Thank you all so much for your attention and your questions.